Machine in your kitchen right now and humming inside every convenience store, office building across world that has not fundamentally changed in almost 200 years. An American invented it, but here's what almost nobody knows. Japan is waging its own fierce battle against the exact same machine. Here is what almost nobody thinks about. The refrigerator and the air conditioner were not invented in Japan, nor in Europe, nor in China. The first working vapor compression cooling machine was patented by a man from Newburyport, Massachusetts, named Jacob Perkins back in 1834. He built a machine that could make ice on demand, and in doing so, he handed the modern world food safety, medicine storage, and livable summers. Nearly 2 centuries later, the cooling units keeping Tokyo and world livable still rely entirely on his blueprint. Now, Japan stands at a critical crossroads, squeezed between brutal summer heat waves, strict environmental laws banning traditional gases, and a strained energy grid. Will the country that mastered the old machine be the one to master its replacement? If you are enjoying videos like this, hit the like button because these take a lot of work to put together. And subscribe so you do not miss what is coming next. While American laboratories in Maryland focus heavily on mechanical hydraulics, rubber-like stretching and squeezing nitinol tubes to escape the 200-year-old vapor compression trap, the intellectual battlegrounds of Japan are approaching the crisis of heat from an entirely different dimension. In the immaculate, hyper-controlled cleanrooms of the University of Tokyo and the sprawling research complexes of the National Institute of Advanced Industrial Science and Technology, AIST, scientists are looking at the same fundamental problem and arriving at a radically different conclusion. Their answer is not a better machine with fewer moving parts. Their answer is a machine with no moving parts at all. This is the frontier of solid-state cooling, and for a nation built on the quiet precision of materials science, it represents a profound national destiny. To understand why Japanese researchers bypassed the mechanical squeeze, you have to understand the core philosophy of Japanese engineering: efficiency through absolute elegance. A mechanical compressor, no matter how well engineered, relies on friction, pistons, valves, and fluid dynamics. It is a miniature engine living inside your home appliance. But solid-state cooling eliminates the mechanical heartbeat entirely. Instead of forcing a fluid through pipes or mechanically stressing a metal tube millions of times, solid-state physics manipulates the internal quantum and crystalline structure of matter itself, forcing atoms to release or absorb thermal energy simply by altering their external environment, be it through a magnetic field, an electric charge, or microscopic crystal transformations. At the absolute vanguard of this movement in Japan are 2 closely related technologies: magnetocaloric and electrocaloric cooling. In a magnetocaloric system, certain specialized rare earth and transition metal alloys possess a fascinating quantum quirk. When you expose them to a magnetic field, their internal magnetic moments abruptly align. This forced orderliness shrinks their magnetic entropy, and as a consequence, the material instantly releases heat. Take the magnetic field away, and the atoms snap back into thermal disorder, greedily drinking in heat from the surrounding air or water. There is no gas seeping into the atmosphere. There is no compressor roaring at 2 in the morning. There is only a quiet, oscillating magnetic pulse interacting with a solid metallic matrix. Electrocaloric cooling operates on a similar, elegant principle, but uses electricity instead of magnetism. Special ferroelectric ceramics and polymers undergo massive, instantaneous temperature swings when subjected to a fluctuating electrical voltage. Apply a voltage, and the crystal dipoles lock into alignment, dumping heat. Release the voltage, and the structure relaxes into chaotic disorder, plunging in temperature. For decades, these effects were treated by Western industries as academic curiosities, fascinating physics demonstrations that could chill a microscopic point on a laboratory benchtop by a fraction of a degree, but utterly useless for keeping a Tokyo apartment comfortable during a 40°C August heatwave or chilling bento boxes in a bustling Shibuya convenience store. The temperature spans were too narrow, the materials too brittle, and the required magnetic or electrical fields too impossibly large for practical engineering. This is where Japan changed the equation, because the country is a global superpower in materials science, honing its expertise through decades of ceramic engineering for bullet trains, advanced semiconductor substrates, and high-frequency electronics. Japanese laboratories began to look at these caloric materials not as fragile lab samples, but as customizable molecular architectures. Instead of copying foreign designs, research teams across Tsukuba and Kyoto began engineering entirely new chemical compositions. They doped lanthanum iron silicon alloys and advanced lead-free ferroelectric ceramics at the atomic level, optimizing crystal grain boundaries to maximize thermal output. They discovered that by tuning the microscopic lattice structures of these materials, they could achieve temperature spikes and drops of tens of degrees, rivaling and eventually surpassing the cooling capacity of traditional chemical refrigerants. Japan's scientific strategy recognized a fundamental truth that the rest of the world was slow to grasp. When you are trying to replace a 200-year-old global technology, you cannot simply build a cleaner version of the old machine. You have to change the medium of reality itself by shifting the entire paradigm from chemistry, trapped gases and synthetic fluids, to physics, solid-state atomic alignment. Japan positioned itself to leapfrog the regulatory traps of global environmental treaties. Yet, translating a brilliant molecular trick from a university spectrometer into a viable commercial product in a resource-constrained island nation is a brutal gauntlet. Because the moment you take a breakthrough out of the clean room and demand that it survive the relentless, brutal reality of daily consumer use, you run straight into a microscopic wall of physics that has humbled generations of engineers. Moving a revolutionary cooling technology from a university spectrometer to a commercial appliance factory is a brutal engineering gauntlet. It is the graveyard of thousands of brilliant physics concepts. For decades, researchers across the globe discovered fascinating caloric materials that could spike or drop in temperature under magnetic fields, electric voltages, or mechanical stress. Yet, nearly every single early prototype shared a fatal flaw. It possessed a heartbreakingly short lifespan. To understand why building a solid-state cooling device is an exercise in extreme frustration, you have to look at what an appliance demands of its core mechanism. A household refrigerator or a commercial air conditioning unit in a Tokyo office building does not cycle a few hundred times. It operates continuously, switching on and off thousands of times a year, enduring tens of millions of distinct thermodynamic cycles over a decade or more of service. Traditional vapor compression systems handle this through brute force. A mechanical compressor is built from heavy steel pistons, thick bearings, and durable motor windings designed to withstand continuous vibration. When a compressor finally dies after 15 years, it usually fails because a seal degraded or a bearing wore down from sheer friction. Solid-state cooling systems do not have friction in the traditional sense, but they face an even more insidious enemy: microscopic fatigue. When advanced alloys, shape memory metals, or ferroelectric ceramics undergo continuous phase transitions, rapidly snapping their internal crystal structures between ordered and disordered states millions of times, the material itself experiences internal trauma. At the atomic scale, no metal or ceramic is entirely uniform. Every sample contains microscopic voids, tiny boundary shifts, or slight imperfections born during the manufacturing process. Every single time the material triggers its cooling or heating cycle, those microscopic flaws experience localized stress. In early solid-state prototypes, researchers watched in dismay as beautiful, high-performing cooling cores developed microscopic hairline fractures after just a few thousand cycles. Within weeks of continuous operation, the stress concentration widened those cracks, and the expensive alloy or ceramic sheared entirely in half, rendering the machine useless. The physics worked brilliantly, but the materials literally tore themselves apart from repetition. For Japanese research institutions and advanced materials labs, solving this fatigue wall became the ultimate obsession. Japanese engineering thrives on longevity. The culture that created machinery designed to run seamlessly for decades without maintenance could not accept a cooling core that self-destructed in a month. To conquer this wall, material scientists began manipulating the microstructure of the cooling elements at a quantum level. Instead of relying on bulk metals that cracked under uniform stress, teams at industrial R&D hubs began developing composite matrices. They embedded active caloric particles inside flexible, high-durability polymer binders, or engineered advanced single-crystal structures where the atomic lattice could shift gracefully without creating stress focal points. By controlling grain growth with extreme precision during the casting and sintering processes, they forced the materials to absorb millions of structural transitions without propagating cracks. Furthermore, engineers had to rethink how thermal energy was transferred away from these solid cores. Because there is no rushing river of chemical gas to carry heat to the back coils, solid-state systems rely on secondary heat transfer loops often using plain, safe water or specialized microchannels that snake directly through the solid matrix, designing these fluid pathways to handle millions of rapid thermal expansion and contraction cycles without leaking added an entirely separate layer of mechanical complexity. The challenge of durability proved that inventing a revolutionary cooling effect is only the first step. The true test of an industrial civilization is whether it can force exotic physics to behave with the mundane, unbreakable reliability of a kitchen appliance. And as Japanese labs in Tsukuba and Kyoto began pushing past the fatigue wall, they realized that solving the material's lifespan was only opening the door to an even greater national imperative, making the technology small enough, quiet enough, and precise enough to fit into a changing society. When you strip away the heavy compressors, the roaring fans, and the miles of copper tubing filled with pressurized chemical gas, you are left with something radical, a cooling system that takes up almost no space and makes virtually no sound. For a nation like Japan, where space is intensely curated and the cultural appreciation for tranquility is deeply rooted, this is not merely an engineering upgrade. It is an invitation to rethink how machinery coexists with human life. In Japanese manufacturing, there is a guiding philosophy known as Monozukuri, the art, science, and spirit of making things. It emphasizes craftsmanship, continuous improvement, and an obsessive pursuit of perfection, particularly when it comes to shrinking technology without sacrificing power. For decades, Japanese consumer electronics companies mastered the art of miniaturization, packing unimaginable computing power into slim smartphones, whisper-quiet laptops, and pocket-sized devices. Yet, while electronics grew smaller and quieter, the thermal management systems required to keep them from melting remained trapped in the 19th century. A traditional vapor compression refrigerator or air conditioner cannot be shrunk beyond a certain physical limit. You need a motor, a compressor pump, expansion valves, and a specific volume of gas to manage thermodynamic cycles effectively. This physical constraint has long dictated the architecture of our homes, vehicles, and appliances. Fridges must be bulky metal boxes. Air conditioners require massive outdoor condenser units bolted to building exteriors. Solid-state caloric cooling shatters these architectural boundaries entirely, because the cooling effect is generated directly within the atomic matrix of a solid material. Whether through magnetocaloric, electrocaloric, or elastocaloric phase changes, the cooling engine no longer needs to look like an engine. It can take any shape. It can be formed into a flat sheet, sculpted into a honeycomb cylinder, or miniaturized into a tiny module no larger than a deck of cards or a postage stamp. This scalability unlocks entirely new frontiers where traditional vapor compression is utterly useless. Take, for instance, the modern data center. As advanced artificial intelligence clusters and massive server farms process billions of parameters daily in cities across the globe, they generate concentrated, ferocious heat in hyperdense spaces. Traditional liquid chilling loops and massive rooftop air handlers consume staggering amounts of electricity, sometimes requiring millions of gallons of water just to keep server racks from overheating. A solid-state cooling core changes the geometry of thermal management. Instead of pumping chilled air across an entire room or forcing liquid through complex external plumbing, a flat, solid-state caloric module can be embedded directly against the microprocessors themselves. It can pump heat away at the exact point of generation, with zero noise, zero vibration, and a fraction of the energy footprint. Consider the electric vehicle. In modern EVs, fast charging sessions generate intense thermal stress inside the battery pack. Managing that heat effectively dictates how long the battery survives and whether it operates safely. Current thermal management systems add significant weight, complex plumbing, and numerous potential failure points to the vehicle. A compact, solid-state cooling element can be integrated seamlessly into the battery modules, conforming to the contours of the pack itself, providing targeted, instant temperature control without heavy compressors or vulnerable refrigerant lines. Even in high-precision robotics, a sector where Japan is a global pioneer, the implications are profound. Humanoid robots and advanced automation systems require tight thermal control for their internal actuators and computing units. Traditional cooling systems are heavy, awkward, and introduce mechanical vibrations that interfere with delicate sensors. Solid-state modules offer silent, vibration-free temperature regulation that can fit into the tightest limbs and joints of a robot without adding dead weight. Furthermore, this extreme miniaturization aligns perfectly with Japan's broader ecological goals. In a society facing a shrinking workforce and a critical need to optimize energy consumption across every sector, appliances that use less power, occupy minimal space, and operate in total silence represent the ultimate evolution of design. Yet, as laboratories in Tokyo and Kyoto successfully demonstrate these postage stamp-sized cooling cores, working with astonishing efficiency on test benches, they face a daunting final hurdle. Moving from a brilliant conceptual breakthrough that fits in the palm of a hand to a mass-produced commercial reality means confronting the giants of global manufacturing and the entrenched supremacy of the 150-year-old compressor. The distance between a triumphant laboratory demonstration and a product sitting on a warehouse shelf is measured in billions of dollars, decades of industrial muscle, and the fierce resistance of entrenched incumbents. For all the elegant physics of solid-state cooling, its material science breakthroughs, and its silent, miniaturized potential, it faces a monumental adversary: the modern vapor compression machine, optimized by global industry for a century and a half. In boardrooms across Tokyo, Osaka, and Nagoya, legacy manufacturing giants, household names like Daikin, Panasonic, Mitsubishi Electric, and Toshiba find themselves standing at a historic crossroads. These companies built their global empires on the back of traditional cooling. They operate massive factories, stamping out millions of highly efficient, reliable, and dirt-cheap compressors every single year. Their supply chains are deeply entrenched, their manufacturing tolerances are calibrated to micrometer precision for copper and steel, and their engineering teams have wrung every possible fraction of efficiency out of the vapor compression cycle. To a traditional corporate strategist, pivoting away from this proven architecture looks like an economic gamble of terrifying proportions. Why abandon a multi-billion-dollar cash cow that runs like clockwork? The answer is that the ground beneath their feet is shifting irrevocably. Regulatory pressure has turned the traditional chemical refrigerant market into a ticking clock. Under international environmental agreements and strict domestic legislation mirroring global phase-downs of high GWP gases, traditional chemical refrigerants are being systematically outlawed. Japan's industrial sector has already invested heavily in transitional chemical alternatives, such as the R32 refrigerant, pioneered widely by Daikin. R32 lowered the environmental impact compared to older legacy gases, but it is still a chemical fluid under pressure, carrying long-term regulatory vulnerability and safety considerations like mild flammability. The writing on the wall is clear to forward-thinking executives. Transitional gases are merely a temporary stay of execution. Eventually, environmental regulations will tighten further, or the economic cost of managing synthetic fluids will outweigh the benefits. When that day arrives, companies that rely entirely on vapor compression will face a sudden, catastrophic obsolescence. This reality has forced a dual strategy inside Japan's industrial research complexes. On one hand, legacy giants continue to refine traditional systems, driving inverter efficiency to astonishing heights and building smart, AI-optimized climate controls for modern homes. On the other hand, they are quietly, intensely funding and co-developing next-generation solid-state and caloric cooling research alongside national institutes like AIST. However, transitioning from research to mass production exposes brutal economic realities. Solid-state cooling relies on exotic materials, specialized rare earth alloys, complex ferroelectric ceramics, or precise shape memory lattices that require hyper-controlled manufacturing environments. Melting and sintering these materials without introducing microscopic structural defects demands specialty furnaces, extreme vacuum conditions, and raw material purity that borders on the absurd. While a traditional compressor is stamped out of cheap, abundant steel by automated assembly lines in a matter of minutes, a high-performance solid-state cooling core is currently closer in complexity to a high-end semiconductor chip. The upfront capital cost of retooling a factory floor to produce solid-state cores at scale is staggering. Furthermore, the incumbent machine is not sitting still. A vapor compression system is cheap, incredibly powerful per unit of volume, and backed by a global network of repair technicians who know how to fix a leaking pipe or replace a worn-out fan motor. A solid-state cooling device must not only match that cooling output, it must do so at a price point that makes economic sense for a consumer buying a household refrigerator or a small office air conditioner. Yet, history shows that this is precisely the friction point where paradigm shifts occur. Every transformative technology, from the early mainframe computers that filled entire rooms to the initial solar cells that were once priced exclusively for satellite programs, began as an impossibly expensive laboratory novelty. They crossed the chasm, not because they were marginally better at the old game, but because they changed the rules of the game entirely. As Japanese industrial leaders weigh the immense costs of retooling against the inevitable arrival of a gas-free future, a quiet realization is taking hold. The race to commercialize solid-state cooling is no longer just a technical exercise, it is a race for industrial sovereignty. The company and the country that successfully scales the solid-state core from a fragile lab bench into an unshakable, mass-produced commercial reality will dictate the thermal architecture of the 21st century. And that race is about to step out of the clean room and into the most ubiquitous retail space in modern Japanese society. Step outside onto a neon-lit Tokyo street on a stifling July evening, and you will encounter the heartbeat of modern Japanese urban life, the konbini, or convenience store. They sit on nearly every corner, glowing brightly through the humid night, offering sanctuary with a blast of chilled air the moment you slide open the automatic glass doors. Rows of refrigerated display cases showcase bento boxes, iced coffees, and dairy products, while overhead, commercial air conditioning units wage a relentless war against the concrete heat island of the metropolis. Right now, that entire sensory experience, the rushing blast of chilled air, the fluorescent hum, the hidden vibration of industrial compressors throbbing behind the back walls, is running on borrowed time. When you trace the arc of this technological revolution, from the foundational 1834 invention of vapor compression by an American tinkerer to the hyper-controlled material science clean rooms of Tokyo and Tsukuba, the ultimate destination becomes strikingly clear. The transition away from the 200-year-old machine is no longer a wild science fiction fantasy. It is an engineering inevitability forced by the unforgiving convergence of climate physics, strict international environmental law, and the sheer thermal demands of an increasingly overheated planet. Imagine walking into that same neighborhood konbini a decade from now. The sliding doors open, and the air inside is perfectly, refreshingly cool. But something is profoundly, wonderfully different. The heavy, rhythmic pulsing of the mechanical compressors is entirely gone. There is no low-frequency vibration rattling through floorboards, no frantic clicking of electrical relays turning heavy motors on and off in the middle of the night, and no background roar of industrial fans struggling against trapped heat. The glass display cases holding your cold drinks maintain their precise, life-preserving temperatures through a network of silent, solid-state caloric modules. Instead of pistons and pressurized pipes, these systems rely on advanced magnetocaloric or electrocaloric arrays, specialized alloys and ferroelectric ceramics quietly shifting their internal atomic structures, absorbing and releasing heat with the serene, frictionless efficiency of physics itself. If a thermal management line were somehow damaged, there is no toxic, high GWP synthetic chemical gas escaping into the atmosphere to trigger regulatory alarms or contribute to global warming. There is no volatile refrigerant hissing into the aisles. There is only a secure, inert solid-state core or a simple, safe secondary loop of plain water. And when the unit finally reaches the end of its exceptionally long service life decades down the line, a technician does not need to extract regulated chemical fluids with specialized recovery cylinders. The advanced metals and ceramics can be safely recycled back into the industrial supply chain, returning cleanly to the materials economy. This is the ultimate promise of the gas-free revolution. It replaces a chaotic system of fluid dynamics, dangerous pressures, and mechanical wear with the quiet, elegant predictability of solid-state engineering. Yet, as we stand on the precipice of this shift, a lingering question remains. The compressor is not merely an appliance part tucked away quietly in a kitchen corner or a convenience store backroom. It is embedded everywhere in modern industrial civilization, humming in the dropped ceiling of your office building, riding beneath the floorboards of your Shinkansen bullet train, regulating the massive battery packs of your electric vehicle, and keeping the artificial intelligence data centers of the future from melting down under astronomical computational loads. The modern world was quite literally built on the back of artificial cooling. Without it, medicine spoils, food chains collapse, and vast portions of the global map become unlivable during the peak of summer. But the machine that gave us this modern life is fundamentally reaching the end of its evolutionary road. You can only polish a 19th century piston and a pressurized chemical loop for so long before the physics of the universe pushes back. If solid-state and caloric cooling scale the way their pioneers envision, these massive, roaring machines will eventually fall completely silent. The ubiquitous hum of the compressor will fade into history, replaced by the ghost of a sound we grew up with without ever truly noticing it was there. The country that masters this silent transition will not merely build a better household refrigerator or a more efficient office air conditioner. It will completely redefine how humanity handles the heat of the future, transforming the most stubborn thermal burden of the industrial age into a quiet, seamless whisper. And that leaves a fascinating question for the years ahead. When the very last compressor finally shuts off, which machine in your life will you miss the sound of the most, and which one will you be happiest to see go silent forever?